Okay, picking up with those left and right limits. Again, we're going to have to do left and right limits even though the problem initially didn't say do left and right limits. We have to be smart enough to do left and right limits because the function is sensitive to greater than and less than 1, and 1's the number that we have in question. So I've got to do left and right. I will try to trip you up by giving you something like this and just expecting you to realize, oh, I got to do left and right. I am not going to guide you through it on a testing situation, that you will just, testing or quiz situation, that you will have to recognize do left and right. So here from the left, same idea. That means x is less than -1. So we use, not -1, just 1. So use 3x. So the first thing I do is replace the f of x symbol with the branch I'm going to use, and then I just substitute and get 3. Similarly, that means x is greater than 1, so we will use x plus 2. So the first thing I do is replace the f of x with the rule I'm going to use, x plus 2, and then substitute 1 plus 2, 3. And now I can talk about the two-sided. My left was 3, my right was 3, so we get to conclude that the two-sided is also 3, because left equaled right equaled 3. And on a testing or quiz situation, if all I saw was this right down here, if all I saw was the answer was 3, you would get no credit, that you're going to have to show me that you reasoned out that why it was 3 was because left equaled right equaled 3. And clearly in a different problem, maybe left and right would be different, and like the previous problem, left and right were different, and so then you would conclude it does not exist. Okay, one more piecewise defined function. Okay, new function, defined a little differently. X squared plus 4 if x is not equal to 2, 5 if x equals 2. Then I have the limit as x goes to 2. So a lot of people say, she wants us to do the exact same thing we did on the previous problem. And it wouldn't be wrong to do the exact same thing we did on the previous problem, but it's not necessary. Because this just means x is close to 2. Doesn't mean it's, that's all we know. It's close to 2, but not equal to 2. That we're getting closer and closer and closer to 2, but we're not going to be equal to 2. Well, there's what we need to know. It's not going to be equal to 2, so immediately that tells us that we can use x squared plus 4, and so we don't have to do left and right, that we can just use the x squared plus 4, just give me 2 squared plus 4, or 8. And so left and right here were not necessary. They wouldn't have been wrong, but they weren't necessary. Not necessary because this function isn't sensitive to left and right of 2. This function is only sensitive to 2 and not 2. On the previous example, we had to do left and right because the function was sensitive to left and right of 1. So the function mandated left and right. But this function isn't left and right. It's just 2 and not 2. Now here we have the left and right limits, But because we know the two-sided, this has to be 8, and that has to be 8, and those both must be 8. Because the two-sided limit was 8. And our very, very important fact tells us that. A two-sided limit exists if and only if both the left and right limits exist and are equal to each other. In this case, all the limits have the same value. So since my two-sided limit existed, that meant the left and right had to exist, and it had to have the same value. So here, no work necessary. We can just do 8. Okay, that ends the piecewise defined function portion of the lecture. Now we're going to move on to trigonometry. Trigonometry has a tendency to be a problem for students, and I wish I had an answer to that, but trigonometry is just required. If you look in my math lab, I have posted under course documents, Trig You Should Know. Trig You Should Know includes the unit circle and various Pythagorean identities. When we're doing trig values, you will always give me exact values, or you should always give me exact values. You're never going to get full credit for decimal approximations. Always give me full values, or give me exact values. So doing some trig here. Evaluate the following. Even when it's trig, the first thing you do when you're doing a limit that's approaching a number is you just substitute. And so I'm just going to substitute. So sine times 2 times 0 plus pi over 4 over cosine times 0 plus pi over 6. And just start working that out. And so that's going to be sine of pi over 4 cosine of pi over 6. Always in radians. If you're using a calculator, make sure your calculator is set in radians. We will not use degrees. Then you need to know these values. Sine of pi over 4 is square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. And so I get an answer of square root of 2 over the square root of 3. That the 2's, the 1/2's, or the 2's cancel. That's a perfectly good answer. You do not need to rationalize denominators for me. And I believe the answers in my lab math, I don't think they require rationalization, but if they require rationalization, rationalize. But for me, you don't need to. Okay, next guy. I'm just going to mark out here that these guys cancel. Next guy. Sine x over x. So let's start by substitution. And that's going to give me 0 over 0, which is indeterminate. You can't make a conclusion about 0 over 0 as a limit. Anybody that makes a conclusion about 0 over 0 as a limit will lose all the points for the problem. All 0 over 0 as a limit tells you is to try something else. Now, our other something else's have been factoring. That doesn't factor. Rationalizing. There's nothing to rationalize there. And then just algebraic simplification. There's nothing to simplify there. So none of our previous techniques are going to get at an answer here. We're just going to look at this graphically, which is not a proof of anything, but it'll give us the answer, and then we will just accept the answer. And so here's the graph of f of x equals sine x over x. And so it's coming right up, and we're going to note here that f is 0, which would be sine 0 over 0, 0 over 0. That's undefined. Because now we're talking about functional values. We're talking about what's exactly happening at 0, and exactly at 0, we get an undefined value, which then corresponds to the open circle that corresponds to f of 0 being undefined. Remember, graphically, when your function is undefined, you're not going to have a y coordinate. You're going to have missing points like that, or maybe you'll find an asymptote, but when a function is undefined, you're not going to have a y-coordinate. But when we look at the graph, and then we think about the limit as x approaches 0, and I take my fingers and I trace either side coming closer and closer and closer to x equals 0, my y-coordinate is close to 1. And so we conclude that it looks like the limit as x goes to 0 sine x over x is 1. Now that's not a proof, but good enough for our purposes. Fact, the limit as x goes to 0 sine x over x is 1, or the limit as theta goes to 0 sine theta over theta is 1, whatever your variable happens to be. Now we can generalize that more. The limit as x goes to 0 of sine mx over mx is 1, and the limit as x goes to 0 of mx over sine mx is 1. You need to memorize this. That should probably say memorize these. What's important here? The argument, your angle, and your denominator match, or vice versa, or the other way around. Your numerator and your argument, your angle match. And when that is the case, those limits are 1. And the reason why we can take the reciprocal limit is because the reciprocal of 1 is 1. So you need to memorize these limits and be able to use them. And we'll end this video here.